Okay, recording. Here you see our new studio, your new classroom. It's my dining room wall, a couple little boards. We'll see how this works. This is for EP physics, and we are learning about motions in the heavens, describing them and trying to explain them. In the last video, we got up through talking about how there were the daily motions of the stars, sun, moon, planets, all towards the west very rapidly, but against that background, slowly, you would see the planets move eastward compared to that. I had a good question on one of the little Zoom sessions I'm going to try to explain real quickly. Somebody asked, I've drawn this map that looked like this, and I had north here and south here, and I had the sun's path, for example, against the background of stars. These are all stars all over this thing. And I said it was moving east, and somebody asked, isn't that west? It is if you're looking on a map, at a map, we're looking down from the outside like a map of the earth. But think about if you're inside a store and you're looking out towards the street through the window, there might be a sign that says Nepo. And you go, what is that? Well, it's open backwards. You see, for a map of the sky, we're using it to look up at the sky sort of from the inside out. So everything is mirror imaged in that sense. So it's actually true that this is, east and that is west. Hope you got that. If you don't, it's no biggie. It does make sense. Anyway, things generally move eastward against the background of stars. Now, I'm talking about the sun, the moon, and the other five things. All those things that the days of the week are named after. Sun day, moon day, Saturn day, etc. So we had established that. I'd also said that Mercury, Venus, Mars, Jupiter, and Saturn occasionally do this little backwards thingy called retrograde, and that's really weird because you'd think they keep doing the same thing all the time, but they actually back up, or appear to sometimes. Furthermore, we had the complication that Mercury and Venus did it while hanging around the sun, whereas Mars, Jupiter, and Saturn do it when they're on the opposite side from the sun. This is just a bunch of weird, complicated stuff. Part of my point is that it's weird and complicated, and it begs and cries out for an explanation. And you should be wanting one, and you'll get some explanations very soon. So we had established all this, and we had not explained any of it. It was just a bunch of facts. We want to find a way to make this make sense, and therefore we need a model. And multiple models got proposed over the centuries. We're going to take it all the way back to Plato and Aristotle, ancient Greeks. They had a model. Not everybody believed the same thing, but starting with Plato, they got this idea. You call this my eraser works here. It's kind of wet. It's going to have to dry a little. But had a geocentric model. Geocentric, means the Earth's in the center. It was obvious to them that the Earth was in the center because everything went around us. You look up in the sky, you see everything going around us. And you probably know from elementary school and just about everything you've ever been taught since that the Earth is not in the center of the universe, that the Earth goes around the sun. You might even know the sun moves. I don't know how much you know about it. But yeah, this is an old, not only out of style, but basically wrong idea. But we're going to explore it anyway because people believed it for 2,000 years and they had very good reason to. One reason to believe the Earth is in the center, besides everything appearing to go around us, is that we don't feel the Earth moving. People very naturally thought, just like you probably would if not told otherwise, that if you're moving, you got to be able to feel it. Now, if you've ridden on a jet plane, sometimes you can sit there and eat. It's all smooth. The ride is smooth. You don't feel like you're moving. And you know what? It's all relative anyway. But people thought that the Earth couldn't be moving because they didn't feel it moving. So, of course, they thought the Earth was stationary in the center of the universe. In fact, I'm going to kind of it's going to have to do for an eraser. So they thought Earth motionless in the center of everything. And there's another thing they thought. They thought that everything went around the world. I'm talking about the sun, the moon, the planets, the stars. Everything went around the world in perfectly circular paths. All the motions of all the wandering bodies were circular. First, because they looked like circles, but also because the Greeks loved circles. Think about how nice circles are. When I draw a circle, I'm not going to try it right now, but when I draw a circle, students judge it. They right away go like, that's not very good. Or, wow, that circle's perfect. What does perfect mean? It means perfectly symmetrical, perfectly circular. A circle is a supersymmetric shape, something where you turn it different ways, you can't tell the difference. And some people like that. Frankly, I like that. I'm a little bit of a symmetry freak. If I were sitting at a table and there were 3 people on one side, including me, and 1 person on the other, I'd get it moved to the other side to even things out. I don't like things uneven. Neither did ancient Greeks. Circles are nice and even all the way around. And uniform. You think of this as 2 different things. Earth motionless in the center, and all motions are circular and uniform. The uniform means nice and steady. After all, it's annoying to see something that speeds up and slows down and turns around. That's nonsensical, and the heavens were the realm of perfection. The earth was believed to be this corrupt place with bumps all over it and bad things happening and everything. But you could always look to the heavens for perfection, like where they don't have coronaviruses, for example. In any case, this basic ancient Greek thought went on for hundreds of years of development. There was another idea. I'm looking at my dog here. There was another idea that the sun might be in the center and the earth might go around it. And there actually were some small groups of ancient Greek thinkers who did think that the sun was in the middle. Nobody much listened to them, and they died. And we barely know that anybody ever even thought it. It got recorded. But by and large, this idea of the earth in the center is what really took off. So, yeah, earth motion in the center, all motion circular and uniform. Different thinkers played with this for about 500 years, and it all came together in the person of somebody named Claudius Ptolemy. Okay, kind of hard to classify what he was, what culture. The Ptolemies were Greeks, Macedonians. Alexander the Great had conquered a bunch of the world within 11 years, came down out of the north of Greece, Macedonia, and then he put generals in charge. He put a general named Ptolemy in charge of Egypt, which he conquered. And so the Ptolemies ruled Egypt for hundreds of years, and then, or a couple hundred years, and then the Romans took over. And so then the Romans are in charge of the Macedonians, who were in charge of the Egyptians. And so he's got a Roman first name, Claudius, and he's a Ptolemy. Not really sure he was in the royal family, some uncertainty with that. But anyway, he lived around 150 AD. So that is 1,870 years ago, almost 2,000 years ago. And what did Ptolemy do? Oh, I guess he had plenty of time to think about such things. Must have lived a comfortable enough life. So he gave all this lots and lots of thought, and he came up with the following system. Basically, it's just putting the final finishing touches on this Greek idea. Here's what he came up with. First of all, the earth was indeed in the center of the universe. And then everything went around it, and he supposed, as had many other people, that there was a great big star sphere. I didn't draw a terribly good circle, see? Greeks would be really upset with that. Anyway, there was this big sphere with all the stars plastered all over it. Just like a big plexiglass thing coated with stars. And it spun on an axis. Like, like that. And the stars would zip around, and it spun, every 23 hours and 56 minutes, because that's how long it takes the stars to come back to the same place. You see a star one night at 8 o'clock over the tree, and you're standing in your driveway, there's the star. The next night at 7:56, 4 minutes earlier, it's in the same place. The next night at 7:52, same place. So you'll see it move westward, during the day, and it takes 23 hours and 56 minutes to do a complete circle. So the stars are doing that. Great, got the stars explained. You can even explain, oh, by the way, they definitely thought the Earth was round. They knew good and well the Earth was round. They knew how big it was. The flat Earth thing, some other cultures thought that. People who weren't educated thought that even later, but no, Western science from a Greek origin knew the Earth was round from way back. It cast round shadows on the moon during eclipses. You can tell the Earth is round. Boats sail over the horizon. They knew how big the Earth was. A guy named Eratosthenes in 250 BC, he was the librarian at the great library of Alexandria, Egypt, where Ptolemy lived, calculated the size of the Earth using shadows from sticks and a well. I won't go into the story right now, but they figured out the size of the Earth and knew it was round. Not a problem, or a problem that was solved. So in any case, how are you going to explain what the sun does? Because the sun shares this quick daily motion almost, but the sun takes 24 hours. All right, so they said that the sun had its own sphere that it lived on, and that its sphere rotated about a slightly different axis. And I know these details are a little bit annoying. Like, do we have to know all this? Well, kinda. I want you to be familiar with it enough so it makes you curious. Like, please make this make sense. Give us a simpler explanation. We'll get there. But at the moment, I'm going to go ahead and say it. Ptolemy thought this axis was tilted 23.5 degrees compared to the axis of the star sphere's rotation. And yet it was attached to it. So the sun was on this sphere. It's kind of on the equator of this sphere that could spin like that, or actually like this, even while it was attached to the big star sphere. So since it's stuck on the big one that's spinning fast with the stars on it, the sun can't help but go along for the ride. So the sun is carried around westward like the stars are. But it does have its own little independent motion, this way, eastward. And it takes a whole year for it to do this. I've got a little bit of an analogy, maybe it'll help. Think of a car tire spinning around. Maybe the car's not even going anywhere. Maybe the car's jacked up on something and the wheel's spinning free. Imagine the wheel is spinning quickly, but some poor bug, spider, was sitting on the tire when it got spinning. You could imagine the tire spinning one way and the spider walking the other way around the tire slowly compared to the tire. Obviously, you're going to see the spider go the same way the tire goes. But if you do a strobe light, if those are, flashing light, kind of drive you crazy. Could even be seizure-inducing for some people. But if you have the strobe light going, and you strobe it so that you flash the light every time the tire spins around, you'll see that the spider is creeping the other way slowly. That's what the sun seems to be doing. You look at the stars, where the stars look the same every night, you'll see that the sun is slipping slowly eastward compared to them. So that's due, according to Ptolemy, to this rotation of the sun sphere, which is stuck on the star sphere. I didn't even motivate the question that's answered by the 23.5 degrees. I'll tell you, it's the seasons. When I drew that picture earlier with that wavy path the sun takes, called the ecliptic, notice it's north in the sky, north of the celestial equator in June, and south of it in December. It's the seasons. And according to Ptolemy, the reason we have seasons is because the sun sphere's axis is tilted 23.5 degrees compared to the star sphere's axis. So the sun is carried off into the northern part of the sky in June, and down into the southern part of the sky in December. And that kind of goes with those pictures. Remember I showed you the Curious George, well, the stars by H.A. Ray, H.A. and Margaret Ray wrote Curious George. He saved them from the Nazis, as I told you. I believe I told that story. Anyway, this tilt makes the seasons make sense. It makes the sun spend some time up our way. And like in June, it's all nice and warm up here because the sun's almost overhead, not quite, and it stays up a long time. In December, it's down south giving them summer and we get winter. So this explains it beautifully, nails it. And he got the seasons explained. So he's got that. Now, what do you do to explain the moon? Well, he knew that the moon could get between the earth and the sun because they saw total solar eclipses. So the moon had to have its own sphere. I know this is getting a little bit small looking. Maybe you can see it. The moon has its own sphere, and it's also tilted kind of like that. And I do not know how he had these things not get in each other's way. It's not clear whether he thought they were actual material, like plexiglass-ish crystalline, actual physical spheres, or whether he thought they were mathematical entities. But somehow the spheres existed in some sense. And the moon sphere was very similar to the sun sphere, which explains why the moon travels through the same general parts of the sky, through the zodiac, those 12 what's your sign constellations. But in any case, the moon took about the same path, but quicker, 27.3 days instead of a year. And he explained it by just having it stuck there. And then, what about the other things, the other wanderers that days of the week are named after, like Mercury, Venus, Mars, Jupiter, and Saturn? He just gave them all spheres. I believe he put, let's see, what did he do? I believe he put Venus's and Mercury's spheres in between the moon and the sun sphere, though I'm not 100% sure. I believe the others, like Mars, Jupiter, and Saturn, had their own spheres further out. But he just had them all attached to the star sphere, and they had to share the daily motion real rapidly westward, like everything else, rising to east, setting to west, or something like that. But they had their own gradual eastward ones. Saturn taking the longest, taking about 30 years. So Saturn's only done 2 laps in my life. Well, there you go. I guess he's explained everything, huh? Actually, not quite. You might recall that planets don't keep going the same way all the time. At least Mercury, Venus, Mars, Jupiter, and Saturn don't. Remember, they do this thing called retrograde where they back up every now and then. Now look at these starting assumptions. Earth motionless in the center. Okay, all motions circular and uniform. Retrograde is a far cry from uniform. Turning around and backing up is not exactly a nice steady walk. Ptolemy had a choice here. He could have just thrown up his hands and said, oh, I guess there's an exception. Every now and then something just backs up. That's very unsatisfying, very unsettling. You're trying to make sense of everything, and that's just nonsensical for something to just break the rules and back up. So he has to come up with a way to go backwards without breaking the rule that you always go forwards. He's clever. Here's what he comes up with. I'm going to erase this again. Hopefully my system keeps working. Okay. So what he does, he comes up with a thing called an epicycle. It's clever. Let's keep writing. So let's just say you've got the Earth in the middle, and you've got a planet that's supposed to be going around the Earth. It could be, say, Jupiter. And Jupiter supposedly wants to keep going the same way around the Earth, but we've seen that it doesn't. Retrograde is where it's moving toward the east, turns around, goes back to the west. Oops, weird. Turns around, goes back to the east again, like it can't make up its mind. He wants it to have a mind that's made up. So here's how he does it. He says, oh, no, Jupiter's not really on its own orbit. Jupiter orbits, says Ptolemy, a point that is on this other orbit. It's an orbit on an orbit. You orbit a point that orbits. It's like this. If I do it with my fingers here, let's see. It's like here's the point going around, and here is Jupiter going around the point while it goes around. Or maybe I'll do it this way, like that. You might imagine the moon going around the Earth while the Earth goes around the sun. It's not quite the same idea, but something like that. So look what happens if you do that. You can get Jupiter to be going pretty fast to the east that way, but it would do whoop-de-whoops like this. That's what it would do. I, as usual, have a couple of analogies. One of them is the teacup ride. I think there's one at Disney World, which is closed now. But the teacup ride, I believe, there's these little teacups, the chairs you see that go in circles, but they're on a big thing that goes in a big circle. So at any given point, as you watch people ride the teacup ride, you might usually see them go the way the main circle is going. But since they're doing their own little revolution there, you'll see them occasionally go backwards just for a bit. Retrograde. Another example, don't know how many of you have these. When I was a kid, I had this thing called Spirograph. It was this kit, toy-like thing, came in a box, had a bunch of paper, had some little pins, like push pins. It had these gear-like things with little teeth on them and some different color pens, that kind of pens and pins. And you would put the pen in the little hole and thing and roll it around the other one. You make little cute patterns like this. Look, it's retrograde just like that. Ptolemy has now explained retrograde without making anybody stop and turn around and back up. Everybody goes the same way. It's just more than one circle. It's a circle on a circle. There was an added bonus to this. Ptolemy realized that if this were true, then when the planet was coming around the inside of its turn here, it'd be closer to the Earth and should look brighter. I don't think anybody had really checked, but he thought, like, what the heck? I'll go look. And so as he observed, he'd see the planets were brighter while they're retrograding. That would be because they're closer then. His model, his little device, the epicycle, not only explained something he already knew, it also had this wonderful added bonus of predicting something he didn't know, and it came true. So he's all big into epicycles. Good. But there's another fly in the ointment, so to speak. I don't know if you know the saying or not. There's another complication. It turns out Mars, Jupiter, and Saturn would do their epicycles whenever the sun, they would do their retrograde part of their epicycles whenever the sun was on the opposite side of the Earth, like a conspiracy. Now, I'm not into conspiracy theories, but this almost requires a conspiracy. You've got to get the sun to be in cahoots with the epicycle so that it always knows to do that, so that it's almost like the sun's hiding behind the Earth while it's retrograding. It just always worked out that way. Ptolemy did not know why. He had no explanation for that. That couldn't have helped him sleep at night. I would lose some sleep over that, I guess, if I were Ptolemy. Why should you have this conspiracy? Furthermore, why should you have Mars, Jupiter, and Saturn do this? Mercury and Venus did something different. Mercury and Venus, it's getting kind of too small to draw here, the details aren't too important, but they were never seen to be far from the sun. They obeyed a different rule. Their epicycle centers had to obey a rule that the center of the epicycle had to remain on a line between the Earth and the sun. This would prevent those two planets from ever straying very far from the sun. Why do you want to prevent that? Because you never see them very far from the sun. I don't know if you've ever heard the phrase the evening star or the morning star. Usually you're talking about Venus. You either see Venus in the evening just after sunset over in the west about to set itself, or you see Venus, beautiful and bright, rising in the east shortly before the sun. Same with Mercury, but Mercury is even closer to it. They never get very far from the sun. Why? Nevertheless, epicycles helped. But there's more. Let me tell you more. The problems just kept cropping up. And I promise I will hurry through these two problems to try to get to my point here. The other problem that cropped up pretty quickly, I don't know if you noticed, when I told the I told the dates of the equinoxes and solstices. See, usually, depends on if it's a leap year or not, but usually spring equinox, March 21st, 20th or 21st. June 21st for the solstice. By the way, December 21st was the winter solstice. In September, the equinox is the 23rd. I'll admit that I went much of my career not really bothering to worry about that or think about it. I figured maybe the seasons are all just the same length. Surely the year would be chopped into 4 pieces. Like, if this is the sun's path around the earth, there's the earth. Surely, here are the 4 seasons, right? Equal length. But they're not. To count the days from September 23rd, when the sun passes into the northern half of the sky instead of the southern, on September 23rd, through until March 21st is usually it's about 179 or 80 days. But from March 21st through to September 23rd is about 185 or 6 days. 5 or 6 days longer north than south. Some spring and summer for the northern hemisphere actually truly last longer than fall and winter. If you think it's a long winter, well, one as long as summer. Summer's a longer season than winter. It actually is. Now, how do you make sense of that? Well, Ptolemy is a creative guy, and he has a way. So here's what Ptolemy says. He says, I know what. I know how to fix this. Like if this were, let's say this were June 21st or something, and this is, let's say I'm going to go this way. This could be September. This is December. This is March. He just says, you know what? I'll just move the Earth over a little bit. There. That'll fix it. It does fix it in a way that would make less fall and winter in the northern hemisphere. But that's spring and summer in the southern. It'd make less fall and winter, more spring and summer, just like we want, right? But look, Earth motionless in the center. He said the Earth was in the center. Well, it's more centered than anything else, but it's not the center. That has to have bothered him. If he's a perfectionist and he believes in heavenly perfection and all that, having the Earth a little off center had to have been annoying. And in fact, he called it an eccentric. Wow, see, I'm up to 27 minutes. I'll shut up in just a few. We're almost done. It's called an eccentric. And it's really annoying because it's not in the center, but he had to do it. So you got the epicycle, which is a little gizmo thingamajig to try to make things better. And it worked. It worked. And an eccentric, and yeah, it works. But it's very disconcerting to somebody who believes the Earth is really in the center. One more thing, then I'll shut up about this stuff. There's the center, where the Earth should have been. It turned out that the planet went faster in December than it went, the sun and anything actually, went faster in December than it did in June. Didn't just look faster, it was faster. Oh, God, that messes with uniform. So he's stuck with circles, but he's broken his own rule about being in the center and fudged it a little bit. And now he's going to make the motion not be uniform, but he desperately wants to pretend it is. So he comes up with this, a place called the equant. And the equant it's your happy place, Ptolemy's happy place. It's not in the center. It's not where the Earth is. It's just out there somewhere. There's this place called the equant. And if you lived at the equant, and nobody does, you can't go there. But if you did, the slower motion in the summer would be apparently compensated for by you being closer to it. And you're further from where it's going faster. If you ever notice you're standing close to it, like the cars going by on the road that are real fast, but if you saw one real far away, but you're going kind of slow, wouldn't really be going slower, just look slower because it's far away. So you could make the motion look uniform. Go to your happy place. See your nice uniform motion. If only you stood at the equant. And it actually was a mathematical device that enabled computations and things. Okay, bottom line is this. Wonderfully successful in predicting positions of planets. If you needed to know where Jupiter was going to be 4 years from next Tuesday, his system would predict it for you. It'd be, as far as anybody could tell, correct. That's wonderful. If you're an astrologer, you can cast a horoscope. If you want calendars, things, or if you just want to see if you can figure this out. It worked. It satisfied the whole thing about trying to explain the motions and account for them, but at a cost. Look at the cost. Complexity. Extra little gizmos and thingamajigs you had to throw in there. And also starting to play fast and loose with, violate, be unfaithful to your own sacred starting assumptions. A model that starts messing around with the things that gave it birth is a model in trouble. Then Ptolemy died, and then nobody really replaced it much for about 1,500 years. I'll tell more about the interim stuff and then what it led to later. But now you've seen how Ptolemy's system worked. I'll post a few questions about that, and I probably won't talk as long tomorrow. Thanks for watching. And Zoom is working. I had one little outage today during my AP class thing, but mostly I got it working. So it's worth popping in. It'll be a good discussion. Talk to you later. Bye.